Welcome to Codex, the second Codex. Today we're receiving a talk from Chris Cox. He studied under Boris Buch at Carnegie Mellon, and he will be joining Iowa State here in a bit. Today he'll be speaking to us about nearly orthogonal vectors. All right, take it away.
Yeah, thanks. Okay, so everything's good. You can see my screen. Okay, excellent. Yeah, hi. So what I want to talk about is a question that's, I guess, been asked in a number of different contexts, but how can n unit vectors be arranged in R to the D so that they're as close to orthogonal as possible? This type of question pops up in a few different places. One, just as we're talking about it, these are called antipodal spherical codes. Spherical codes just being arrange points on the sphere so that they're as far apart as possible. And by forcing the code to be antipodal, that is saying that I have x and minus x always in my code, that's actually forcing the vectors to be as close to orthogonal as possible. If I think about x and minus x as the same point, in other words, in projective space. But these are also very closely related to balanced error correcting codes. If I think about a code in the Hamming cube as a bunch of plus minus 1 over root d vectors, well then close to orthogonal, having very small inner product, is equivalent to having Hamming distance close to d over 2 if you do the computation. And these types of codes are very desirable. Both they're far apart, they have large distance, and also it's very symmetric. In this talk, oftentimes we care about these types of configurations, these spherical codes, when the number of points is very large compared to the dimension, such as exponential in the dimension. But today we'll focus on the case when the number of points is only slightly larger than the ambient dimension that they're living in. So think d plus 5 points or d plus 100 points, but not even 2d points today. So a quick definition, just so we can move everything together. We'll just use theta of dk to be this minimum inner product over all of these. So in other words, I can look at some arrangement of vectors on the sphere, and I can ask how close to orthogonal are they? And the measurement of how close to orthogonal is just the maximum inner product in absolute value. The closer this is to 0, the closer the vectors are to being orthogonal. And I want the best configuration of d plus k points in R to the d. So this is exactly the metric. I have k extra vectors in Rd on the sphere, and I want to know how close can they be made to orthogonal. And this theta dk is exactly this measurement. And as I said, we're only considering when the number of points is fairly small compared to the dimension, fairly close to the dimension. So we'll think about k being some fixed number and d tending toward infinity. Even though in a lot of these results, you can let k grow with d, let's just think about k being fixed. So just some easy results to make sure we're all on the same page. Theta of d comma 0, well, now we have d unit vectors in R to the d, and how close can we make them to orthogonal? Well, we could have an orthogonal basis, so this theta d0 is going to be 0. We can actually make them all orthogonal. If we move on to theta d1, well, this is arranging d plus 1 points in R to the d so that they're as close to orthogonal as possible. And it turns out the best thing to do is to take a regular simplex. And if you do the computations, you'll find out that all inner products are negative 1 over d. And because we're taking absolute values, we'll get 1 over d here. Technically, the regular simplex would only give us an upper bound. I'll prove the lower bound to you in a moment, although in a special way, even though there are lots of ways to prove this. But we can actually use the simplex to get a kind of general upper bound, provided that k is, say, fixed and d is tending toward infinity. Theta of dk is going to be at most k over d, because I can think about stacking a bunch of simplices orthogonally to each other in these dimensions. So I'll think about having a d over k dimensional simplex, break up my space into into k pieces of dimension d over k, orthogonally stack up a bunch of simplices, and we'll get that all inner products are at most roughly k over d in this picture. So these are all kind of upper bounds-ish. lower bounds, well, there's what's called the Welch bound, which has kind of been rediscovered and is a very simple inequality that's been known for a while. And it follows just from Cauchy-Schwarz using Cauchy-Schwarz on the eigenvalues of a matrix A. And it's just this lovely inequality where the trace of a matrix squared is at least the trace of A squared divided by the rank of A for symmetric A. If you just plug this inequality in, this inequality is just Cauchy-Schwarz, and you'll crank through it and find the Welch bound. The thing to notice about the Welch bound is, again, when k is small compared to d, it's telling you that, well, theta of dk is at least roughly square root of k divided by d. And compare that to the upper bound of k. All right, questions so far? Or I guess just unmute yourself and speak up if there are any questions. So what are some new results? Well, we knew theta d1 was 1 over d, and we can actually compute theta d2 exactly as 3/2 over d. I'm just writing squigglies. We actually know the lower order terms as well, but we'll just write squigglies and do asymptotics throughout this because it's easier. And compare that to the Welch bound, which is giving you a lower bound of about square root of 2 divided by d. So it turns out the Welch bound isn't actually tight for d plus 2 vectors, and it's actually 3/2 is the right answer. And in general, we can improve on the Welch bound by saying it's at least asymptotically some constant depending on k divided by d with this kind of messy looking constant over here. Now, this constant looks like a mess, and it is a mess. And if you look at kind of how the constant is growing asymptotically, say k gets large, turns out it's growing like square root of k plus 2. So remember, with the Welch bound, it's square root of k, and we're basically improving this to square root of k plus 2. Now, this kind of feels pointless. Why do we care about this extra plus 2 inside of the square root? Well, it turns out that this weird number, this is a tight bound whenever k is, well, 1, 2, 3, 7, or 23. This is perfectly tight, at least for infinitely many d. And furthermore, it's an improvement over the Welch bound and the best known general lower bound as long as k is at most some constant times the square root of d. So for k between 2 and some constant times square root of d, we do get a strict improvement. Another thing that I'm not going to talk about today, I'm going to focus actually on this lower bound, is that actually square root of k over d is asymptotically correct. So for large enough k, you can always find arrangements of d plus k vectors that's at most like 1 plus epsilon times square root of k over d, close to being orthogonal. We get even tighter results for unit vectors in the complex space. So we could think about exactly the same problem over the complex numbers instead of the real numbers. And all of these results translate very naturally to that setting. There's very little that's special about the real numbers. All that changes is this alpha k changes its value slightly. And we get even tighter results in the sense that it's perhaps tight for all k. We don't know for sure. It's related to an open question that I'll mention later. And last thing that I at least like about this bound is we don't use the Delsart linear programming method at all. It turns out that you can actually prove our result by using it, but you don't have to. And it's interesting because the Delsart linear programming method is basically one of the only ways we know how to get bounds on these types of codes.
Can I, just pipe up here?
Mm-hmm.
So it's really weird to me that like the excess number of vectors you get tightness for are like the numbers that one gets for the dimension where you have like a maximal real equiangular tight frame. Is this like some sort of duality thing?
It is. It absolutely
okay, gotcha.
is. So we'll talk about that. And that's why theoretically we're tight for all k and c, because we always have these the maximal equiangular lines, possibly, no one knows. But yes, there is absolutely a duality between these two problems. Absolutely.
Thanks.
Okay, sorry, I think things froze. Am I okay? Can someone?
Can hear you.
Okay, you can hear me. Can you see things?
Yes.
I can't see myself. Okay, sorry, Zoom's just being weird. All right, but as long as you can see things, that's great. Okay, so I want to give you a proof that theta d1 is at least 1 over d. And there are tons of proofs of this. In fact, the Welch-bound work to prove this. But I want to give you a proof that'll generalize. So let's start out with d plus 1 vectors in R to the d unit vectors, where all of their inner products are at most epsilon in absolute value. And we want to say that epsilon is at least 1 over d. So we'll look at the Gram matrix of this thing. And now the Gram matrix has rank at most d, but it's d plus 1 by d plus 1, so it has a non-trivial kernel. There's some vector little a that's inside of the kernel of this matrix M, some non-zero a. So what I'm going to do is I'm going to look at the equation ma equals 0, and I'm going to look at the ith row for some I. There are d plus 1 rows I can look at, just look at row I. And if we write out that equation, we get 0 is this. We can expand out just in terms of what this product looks like. And now what I'm going to do is I'm just going to pull off the ith guy, because I know the inner product of vi with itself is 1. And I'm going to leave the others altogether. Now what I can do is I can move the AI over to the other side. So go move this guy over to the 0, take absolute values, and apply the triangle inequality. And by using the triangle inequality, I know that all of these, when I is not equal to j, are bounded above by epsilon. So we're going to get this inequality that holds for all I. Well, because this inequality holds for all I can just pick the largest coordinate of A. I can say that AI is the largest coordinate of A, and then just take these guys and upper bound them by the absolute value of AI. We'll wind up getting that the size of absolute value of AI is at most epsilon d absolute value of AI, which then gives us that epsilon is at least 1 over d, because A was non-zero. So there is a proof that theta d1 is at least 1 over d. And the piece that's really important about this proof is this inequality right here. So let's think about what happens when we are looking at, say, theta d2. So now we have d plus 2 vectors in R to the d. Well, we can actually play the same game. We can pick any vector we want in the kernel, and any one of its coordinates I, and chug through this same sequence, and we'll get that this inequality, absolute value of AI, is at most epsilon times the sum of the rest of them. And just because I'm lazy, I'll just say that's approximately d times the average over all of those. So if we solve out, this times epsilon. I forgot an epsilon. Great. All right. And if we solve out for epsilon, we get this expression. So because this is a 1 over, in order to, we want to say that epsilon is bigger than or equal to something. Well, this wasn't only true for a single vector in the kernel, it was true for any vector in the kernel and any coordinate I looked at of that vector. So I might as well maximize over those. And if we look at what happens here, for theta d2, proving it's at least 3/2 over d, we would then want to show that this quantity inside of here is at most 2/3. Now, that seems kind of hard because, well, I'm minimizing over the kernel of M, and then I am minimizing over a choice of coordinate of that vector. That's a bit of a weird thing to be doing. First off, I have no clue what the kernel actually looks like. And then, well, even less so do I understand what the coordinates of a vector in the kernel look like. So let's try to unwrap this a bit. Well, first thing, again, my Gram matrix is a d plus 2 by d plus 2 matrix. And again, its rank is at most d. So I do know that the dimension of the kernel is at least 2. So let's just say, without loss, it's equal to 2. So the kernel is the span of 2 vectors, x and y. So for any vector inside of the kernel, A, its ith coordinate is, of course, a linear combination of the ith coordinate of x and the ith coordinate of y, which, if I think about the linear combination as being alpha beta, I can think about this as the inner product between the vector alpha beta with the vector xi, yi. So let's think about it this way. instead of just thinking about I have the vector x and I have the vector y, which span my kernel, and I'm looking at linear combinations, I'll think about breaking these vectors up into their coordinates and inserting them into new vectors. So x1, y1, well, those are the first coordinates of x and y. x2, y2, second coordinates. And I'm going to think about this as a point set that lives, well, in R squared. One thing to notice is it could be a multiset. There's no reason that x and y can't share some coordinates and see coordinate pairs many times. It could be that some of these points are 0, I don't know. But now this becomes, we can change this problem very slightly. Now I have some arbitrary point set in R2, multiset possibly, and I want to minimize over my choice of Q and minimize over this alpha beta, a linear form on this point set of this expression right here. This is just rewriting optimization over the kernel and saying, well, the kernel really is just giving me some point set in R2. Unfortunately, I don't know anything about this point set except for the fact that it spans R2, because of just, that's the rank of this kernel. So this is what we want to prove. We want to say that P is an arbitrary multi-point set in R2 that spans R2. And I want to show that I can find some point in the point set, some vector in R2, so that this weird thing is at most 2/3. So this is some sort of deviation from the mean. This is kind of a normalizing factor. And then I want to say that up to some normalizing factor, I can find a vector which is pretty close to orthogonal from every other point in my point set. So let's prove this. So what I'm going to do is I'm going to think about throwing my points down in R2. And all I know is that they don't all lie on just a single line. And I'm going to look at their convex hull. And now I'm going to use a nice theorem, I believe, by Besekovich from a while ago that says that I can circumscribe this convex hull with a general linear image of a regular hexagon. Now, technically, I'm cheating here. It needs to be centrally symmetric. Otherwise, I could only get away with an affine image. But OK, it doesn't really matter. Double up my point set and flip it to force it to be centrally symmetric. It won't actually change this problem. And now we notice a fundamental property of this weird expression is that it's invariant under changing P by a general linear image. Now, this is pretty easy to see just from the expression. I can pass the general linear transformation across the inner product. But kind of more conceptually, it comes from the fact that this point set came from picking an arbitrary basis for the kernel of the Gram matrix. And by multiplying by a general linear transformation, it's the same as just picking a different basis for the kernel. But what this means is I can apply a general linear transformation, not change my problem at all, but make this hexagon that circumscribed it regular. So it looks like this now. And what I can do is I can look at a few things. So one, let's just look at the normal vectors to these lines right here, v1, v2, v3. And because the hexagon circumscribes the convex hull, I know that I have points on each of these lines. On each of these edges, I actually have a point. So now let's look. Well, consider any point inside of this hexagon. I don't know, maybe this point. If I look at this guy right here, it's at most 2. This is a simple convex optimization problem. I know that the optimum must occur at a vertex of the hexagon, and there it has value 2. And because all the points live inside of the hexagon, I know that the average over all my points is at most 2. And Pigeonhole lets me pick out one of these vectors so that the average is at most 2/3. And now the point is that I know that I have this, say, Qi that lies on that same edge. So this guy right here is just going to equal 1. And hence this average, this weird expression right here, is indeed at most 2/3. Just kind of by a pigeonhole and using this hexagon. And it turns out that this is tight if I can reverse engineer all of these steps to wind up, basically take the hexagon here and reverse engineer everything in order to get a construction for the original problem. So now what's going on in general? Well, we only did it for k equals 2, but the moral of the story continues. We can play exactly the same game of optimizing over the kernel, except now the kernel is k-dimensional. So in order to find lower bounds for theta dk, so that's k extra vectors in r to the d, we get this problem right here where we have some arbitrary multiset of size d plus k, which spans r to the k, that's all we know about it, and we want to minimize over linear forms of this expression right here. Well, just because, again, I said that k is fixed and d is tending toward infinity, so I'm lazy, so I don't like the fact that I have possibly multisets. I really don't like that. So I'm just going to replace multisets by measures, because as d goes to infinity, they're indistinguishable. So just to make life easier for myself, what we care about is given any probability mass on r to the k, so that its support spans r to the k. I don't want it to be concentrated on a subspace. We are trying to look at all vectors in the support of mu and trying to minimize this expression over all linear forms. That's our goal. Again, as long as we have upper bounds on this, we get lower bounds on the original problem. So there are a couple issues. We don't have any clue what this measure mu looks like. All we know is it supports spans r to the k, but that's really not much. Take any measure and jiggle it a little bit and it'll span r to the k. But even if we did know what it looks like, how could we possibly select this v and this y? Well, in R2, we use the hexagon to give us all of the power. And we use the hexagon to give us all the power and to make everything work. Unfortunately, that same idea will not work in higher dimensions. At least I don't see any way it will. The hexagon is very, very special, and the properties it has really don't extend to higher dimensions in that same way. So, well, we can still learn a couple things about the two-dimensional case. Namely, we can say a little bit about mu because this problem is invariant under general linear transformations. We can push mu by an element of GLK. So why don't we find some general linear transformation so that the push forward of mu looks nice in some sense? And then, well, I don't know how to actually pick v and y smartly, so let's just average. At that point, just average over all v and y because I'm dumb. Why not? Okay, so
Quick, do you lose something when you average?
So in general, I don't know. In the cases that are, that I claim that we have tight results, we lose nothing because, well, we have tight results. You lose. It's not just that we have asymptotically tight results, we have exactly tight results, so you lose nothing.
Great, thanks.
Yeah, but in general, when we don't actually have optimality, it's unclear whether or not you lose something by the averaging. I don't know the answer to that. I'm sorry, Dustin. In general. All right. Okay. So what does it mean to look nice? Well, it took us a while to figure it out, but this is what it means for us for a probability mass to look nice is something called isotropic. So probability mass is isotropic if, I think this is the more helpful one, this is essentially the covariance matrix if you don't actually care about subtracting off the mean. So we're essentially saying that the covariance matrix is some multiple of the identity. And the correct multiple to pick is 1 over k. It's also the same as saying that it essentially, in an L2 sense, is equally distributed throughout space. Another word for these that we didn't know when originally writing the paper is these are called type frames or probabilistic type frames. But the fact that they're possibly probabilistic doesn't matter much. So what's important about these isotropic measures is, well, if the support of mu spans all of r to the k, then it's a very simple linear algebra exercise in diagonalization to show that there is some general linear map which will change mu into an isotropic measure. So no matter what measure you give me, provided its support spans everything, I can force it to be isotropic without actually changing the problem. So now we can just concentrate on the isotropic measures. And if mu is isotropic, then this quantity we care about, we can actually get an upper bound. And this is doing exactly what I said by instead of trying to select v and y, just average over all possible v and y. And we'll find out that the quantity that we care about is at most what looks a lot more nice to me, a certain first moment of an isotropic measure. Namely, independently select x and y from your measure and look at the absolute value of the inner product.
So I have a quick question. You
Mm-hmm.
might not know this since you're not super into like probabilistic frames, but is the trick to turning like a measure where the support spans Rk into an isotropic measure, is this the same sort of trick that we would call in frame theory parcellization? So you would like take the expected value of that XX transpose, and that should be positive semi-definite, and then you take like the square root of that, and then you take the inverse of the square root of that, and then apply it, and that's your Q?
Yeah, absolutely.
Awesome.
Yeah, it's as I said, like a diagonalization thing. We can factor this out right into some like d lambda d transpose, right? And then just break the lambda up into two pieces, right? Exactly. Yep, so that's all that's going on here. Are we happy with that?
Yep.
Okay, yep. And here, if you just honestly do the averaging, average over, well, pick, in fact, we're doing even more here. We're not just averaging, we can't average over all V, right? I mean, that's silly. So how are we going to average over V? In fact, we're just going to pick V equal to Y. Why? Why does this work? I don't know for sure. The reason we did it is because it at least made the expression that we wind up with look nice. So now, instead of having to do some nasty optimization problem about, you know, minimizing over all linear forms and blah, 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 all we have to do is upper bound essentially a first moment of isotropic measures. And that at least seems easier to me. And that's what we do. So, turns out that for any isotropic measure, mu on r to the k, if I look at this first moment, it's at most 1 over that really silly looking alpha k from the beginning. And I'm going to write 1 over alpha k in what probably looks like a bit of a weird form here, unless you, well, I mean, people like Emily know what's going on, so probably doesn't look that weird.
I actually have no idea where that's coming from, so.
Oh, well, okay, we'll see in a second. And we get equality in this thing if and only if mu is uniform on a system of k plus 1 choose 2 equiangular lines. So what are equiangular lines, just so we understand these things? Well, it's a collection of equiangular lines is just a bunch of lines that go through the origin, and they all intersect at the same angle. So of course, working with an actual line is a bit weird, so let's just work with unit vectors that span the lines. So we'll just say a set of unit vectors is a system of equiangular lines if they're all unit vectors and the pairwise inner products are the same in absolute value. So they're all plus or minus some fixed beta. Now, we'll come back to this page in just a moment, but two famous examples of equiangular lines are, well, 3 equiangular lines in R2 are formed by the lines that pass through opposite corners of the hexagon. That's actually why the hexagon was showing up in our R2 proof, even though we didn't use any facts about equiangular lines in that proof. Turns out that this is what was so special about the hexagon as well. Hexagon is just super special. And in 3 dimensions, you can get 6 equiangular lines by looking at the lines that pass through the opposite corners of the icosahedron. And Grison's theorem says that if I have a system of equiangular lines in Rk, it has size at most k plus 1 choose 2. This is a very short proof. And we know that we can achieve equality when k is 1, 2, 3, 7, or 23. We don't know about any other values of k, but we do know that that if we can get equality, it's heavily restricted values of k. Some people think that these are the only values. I really don't know. A quick comment. So we see these are, you know, the dimension 2 and the dimension 3. the dimensions 7 and 23 actually are coming from the E8 lattice and the Leach lattice, one dimension higher. So if we actually go back to where this number is coming from, well, let's think about if mu is actually uniform on a system of k plus 1 choose 2 equiangular lines. Turns out that you can compute that this right here, 1 over square root of k plus 2, this is the common inner product for a system of k plus 1 choose 2 equiangular lines. It's 1 over square root of k plus 2. So here what's going to happen? Well, most of the time, if I pick x and y independently, I'm going to get, x and y being different. So that's 1 over square root of k plus 2, except on the diagonal, when I actually pick the same one. There I'll get 1, so I should modify that out. And the probability that I actually pick the same vector is 1 over k plus 1 choose 2, because that's how many vectors I have. So this expression is coming from exactly what you would get from this system of equiangular lines. And it turns out that whenever we actually have this maximum system of equiangular lines, we can actually reverse every step of our proof and wind up with constructions back in the original problem of arranging d plus k unit vectors so that they're as close to orthogonal as possible. So we can always reverse engineer in these special cases and get matching bounds. So every inequality we wrote is actually equality. Last comment is everything we said works also over the complex numbers, except there you're dealing with systems of equiangular lines over the complex numbers, which can have size at most k squared. And these numbers change a bit. For instance, the k plus 1 choose 2 turns into a k squared, and the 1 over square root of k plus 2 turns into a 1 over square root of k plus 1. But then everything goes through, and again, we get equality if these systems exist. And we know that these systems exist for many, many k over the complex numbers, possibly all of them. We have no idea. Of course, the numbers for which we do know they exist, it depends on whether or not you're a mathematician or a physicist, I guess. But yeah. Anyway. So yes, as I said, whenever there is a system of k plus 1 choose 2 equiangular lines in RK, we get matching upper bounds on theta d k. Everything is tight. So a few questions that we don't know. The first case, so we've answered theta d1, theta d2, and theta d3. We don't know theta of d4, so d plus 4 vectors in RD. The best bounds here are 2.13, like whatever our bound gets out here. And the best construction that I had gives you about 2.4 over d, which I believe comes from essentially reverse engineering the proof using maybe the 16 cell as the measure in the dual. But what's interesting is, so this again is the expression that we cared to optimize. We needed upper bounds on it over all measures mu. And none of the regular 4 polytopes actually optimize this. So I plugged those in and they're not even local optima for this problem. So it's unclear what the optimizer of this kind of dual structure even looks like for this 4-dimensional problem. It's unclear. So a natural extension of this problem is to change antipodal codes to actual codes. So now instead of asking how close to orthogonal can we make the vectors, let's just say how far apart can we make the vectors. So that's the same as just trying to minimize the absolute value without, minimize the inner product without taking absolute values. Make this as small as possible. And well, okay, if I have fewer than 2D vectors, this is a bit of a silly question because I could take plus or minus the standard basis. That's a bit silly. So now we'll say that we have like k extra vectors compared to 2D to force this inner product to be positive. So as far as I could tell, I threw it into my computer a bit, but the Delsart linear programming techniques seem to only be able to prove a lower bound on this problem of roughly k over d squared. But with Igor Bala, who I think is still at ETH Zurich, we can actually prove a lower bound of some constant times the cubed root of k over d, which is changing this d squared into a 1 over d. And the upper bound we have is some constant times square root of k over d, which comes from this problem right here. theoretically, it should be the case that the best thing to do for these 2D plus k vectors is to take an antipodal code, and then like actually that and its negatives should be pretty close to optimal. Unfortunately, it's not always optimal. For 2D plus 2 vectors, actually a simplex and its negative are not the optimizers. It's not even locally optimal, which is a bit weird. But it should be pretty close to optimal. I just don't know how to show anything like that. So the game here would be to change this cubed root of k into a square root of k, which would be interesting. I don't care much about the constants at this point. And that's all I have to say. So let me know if there are any questions. Yeah, that went quite a bit